that you had from the quiz. So it goes like this. We have 4x squared minus y squared equals c is a one parameter family of solution. Of a differential equation that looks like this. Y dy dx equals 4x. Okay, there are two parts. The first part is we want to find the implicit solution subject to, so find an implicit solution subject to some initial values. So in this case it will be y valued at 0 equals -7. This part was not really a big of a deal. You want to find basically a value of c, but also you need to sketch it. So let's sketch it and say 4x squared minus y squared equals c is really a family of hyperbola. So it's an hyperbola, or hyperbola. Actually, a family of hyperbolas. Let's be more specific. So hyperbolas, let's so how it looks like. One way to look at it, especially when we consider the this is y evaluated at 2 equals -7, not y evaluated at 0. So you look at this hyperbola, it has two branches. One branch will be this one, and the other is this one. Okay, but we also know that subject to the initial values, y valued at 2 equals -7. So let's say there is a point right here which is 2 and -7. What does it mean? Well, the graph of the relation, which is the hyperbola, well, this is not really a function because it doesn't pass the vertical line test, but the relation or the hyperbola has two branches because it's subject now to the initial values 2 and -7. We ought to disregard this branch. So we eliminate that and we say this branch is not part of the solution. So the upper branch is not part of the solution. Subject to y valued of 2 equals -7. Go ahead.
Question. When you say find the implicit solution will be both. Then
there is a difference between implicit and the function.
I mean the explicit. The explicit is just the lower part, right?
No, it's still the implicit. You'll see the solution. It's still going to be implicit solution, but a solution cannot be both branch. We talked about it.
If I remember well, in the question in the quiz is find the explicit solution, not implicit.
The question in the test and for part A is find an implicit solution subject to.
So if it asked implicit,
you're talking about part B.
If it asked you to sketch an implicit function, then you would do both. But if it says solution, then it's just one of them.
This is, we talked about the difference between function and solution, or relation and a solution. the function or a relation can have multiple branches, but a solution, because we look at a curve, can be is subject to some initial value, cannot be in both. If in this case, if y is negative, then it cannot be positive. Okay, there is no way that y passes through, that the graph passes to a -7, that will to be included in the upper branch. So that's why only this is the solution. Now to solve it implicitly, now what we'll do, we replace x equals 2, y equals -7 in order to calculate c. Okay, so we calculate c and we said, okay, 4 times 2 squared minus -7 squared equals c. And therefore c equal 16 minus 49 equals -33. And the implicit solution, this is for you, Lou, the implicit solution subject to y of 2 equals 7 is given by 4x squared minus y squared equals the specific value of c, which is -33. Like so. Okay? So that was the first part. Go ahead, Dylan.
So implicit function will equal a constant value, right? And I understand that difference between that and an explicit function. What's the graph of an explicit solution look compared to?
Let's look at it. That will be the next part. So, what happened on the next part? The next part, part B, we want to find an explicit solution passes through the origin. So again, the solution, this time we're going to, at the origin, xy equals 0, 0. So substitute I did not spell substitute correctly. There are 3 t's, I have only 2. We'll substitute xy equals 0, 0. In the solution, in the implicit solution. So what do we have? We have 4 times 0 squared minus 0 squared equals c. Therefore, c has to equal 0. So the implicit solution is going to look like the implicit solution is 4x squared minus y squared equals 0. So we solve explicitly. So for y, and get y squared equals 4x squared, and therefore y equals plus or minus 2x, right? And this is the explicit solution. So how does it look like? Well, y equal 2x is this one, and y equals negative 2x is this one. And it passes through the origin as advertised.
So the explicit solution is just in this case, it's just two lines, but if we were to look at the implicit solution, it'd be that family of hyperbolas, or just that one lower one from that family of hyperbolas.
It depends if you have a value of C or not. If you have a specific value of C, then it will be just one curve. If you have C in general, if you have the one parameter, then it's a family of curves. Now notice that these two lines actually some sort of hyperbola, except it's redundant. It's not an hyperbola, two lines, because you have to have square. But if you have plus minus 2x squared plus minus 2x squared, 4x squared, how does it look like? It's two parabolas, but two parabolas, when you bring these two branches together, you have plus minus, you have two parabolas. It's not exactly parabola, still the difference is this is parabola and this is two lines, but you see how we reduced it. All right, so this was the quiz question. Let's go back and talk about what we started last time. We talked about autonomous first order differential equation. Yeah, go ahead.
Yeah, in that quiz question, there was also a part asking like the interval of the solution.
Yeah, well, you can see from the graph here, from either graph, the interval of the solution, x, there is no restriction, it goes from negative infinity to infinity.
In the previous, we also stated the intervals of the y's. Why here we only talk about x?
Because there are two things. They ask you about the interval of solution. Those interval of solution normally refer to the interval of the independent variable. A region, if they're talking about the region where you find a solution, that will be a region. So you have to give boundaries for both x and y. Okay. All right. Autonomous differential, first order differential equation. I gave you the definition last time. Let me recap real quick and go ahead and discuss this topic in more details. So the definition, it's more like a description than a definition. An autonomous first order DE is a function of y only. For example, y prime equals f of y, or dy dx equals f of y. And last time I gave you a couple of examples. One was autonomous and the other is not. I don't know if you remember that. Let me show you what we had last time. Here's the two examples. I gave you y prime equals 10 cosine squared y. This is a nonlinear autonomous, but the y prime equals x cubed minus 10x cosine squared of y is not. Okay? And you see at the bottom we also defined critical points. So let's do that. So here's another definition. Critical points in calculus 1 were value of x for which y prime equals 0. In this case, we're talking about autonomous. So those are points for which, or in which, or for which actually, y prime equals 0. Same way. Those are values because equals only f of y, then it will be only values of y. And here's the first exercise. Let's find critical points. I call it CP for y prime equals y times a minus by. Okay? This is a rather famous differential equation. The solution, part of the solution, is something called logistic equation. First of all, here we'll write that A, B are both positive. So let me tell you a little bit about the solution of this equation. This is important, as I said, important differential equation. So what is a logistic equation? Well, when we learn about exponential growth, we know that the function, the exponential growth function is some constant c e to the power of et, right? And this function, if c is positive, this function is increasing all the time. The question, will it increase or to what end? Will it decrease to infinity? Well, yeah, if c is positive and the function e to the kt and is positive and is positive, right? As t goes to infinity, c e to the kt will go to infinity as well. Now, do we have, in reality, a situation where a function increases exponentially with no end? Only if something blows up, right? But if you look at the model of population growth, and you want to model it exponentially, you want to say, wait a second, this exponential growth function is not entirely realistic. There must be some limiting factor, right? You cannot grow to the end of time. For example, you take an island, a large island with all the vegetation, and you put a couple of rabbits, male and female, right? And no enemies, no predators, nothing like that. So they're gonna multiply, right? Rabbit has a very, very intensive sex life, so they multiply quite rapidly. But will they multiply to infinity? No. Eventually, the island can supply so much resources for the population of the rabbits. So it will start not at zero, really, to start with two, a male and female, but we'll end up at a certain number, which is the maximum number that can be sustained by the resources in the island. And this is going to be something called limiting capacity of the exponential function. That's a logistic equation, typical logistic equation. So we are going back to this, and we'll talk about the logistic equation a little bit more as we analyze this type of function. For instance, so let's see what are the critical points. Well, the solution is very simple. We let y prime equal 0. Therefore, we look at y times a minus the quantity a minus by equals 0. This happens when y equals 0, or when a minus by equals 0. And the result, this will happen when y equals a over b, right? So the two solutions, y equals 0. So one critical point is y equals 0, and the other is y equals a over b. Now a over b, if a and b are both positive, then a over b are positive. So now let's look at the graphic interpretation of this exercise. What does it mean? So let's say you have, this is the y value, the y-axis, and here, let me dot it, is the x or the t. Remember, those are interchangeable values. So this is the x value. We have two critical points. Now, critical points are value of y. We don't know anything about the value of x, right? This is true for any value of x. Y equals 0 is a critical point, regardless of what is the value of x. So, and the same with y over b. So this line correspond to y equals 0. And let's draw another very horizontal line. This line here, this one will correspond to y equals a over b. Both are positive. Let's say both are, let's say a equals 2, y equals 1, right? I'm sorry, a equals 2, b equals 1. So this will correspond to y equals 2. So what we know that the derivative y prime equals 0 when y approaches a over b or y approaches 0, correct? Notice that we can divide y into 3 regions. For instance, here on the top, y equals a of a, y, I'm sorry, not but y is greater than a over b. Here, y is greater than 0 but less than a over b, and y is less than 0. The question is, what is the value of y prime? At least how y prime behave. We don't know the exact value because we don't know the exact value of a and b, but we can tell whether it's positive or negative. We can tell whether the function is increasing or decreasing, correct? For instance, let's look at, well, to better analyze it, let's do this. Let's say y prime equals y times a minus quantity a minus by. Let's factor out b. So it would be by times a over b minus y. Okay? Like so. And let's look at 3 cases. Region 1, y is greater than a over b. What happened to y prime when y is greater than a over b?
It would be negative, right?
It has to be negative, right? B times y is positive because b is positive, y is greater than over b, it's positive. And y is greater than over b, so y prime is negative. What does it mean? It means that the function or the solution has a negative slope that eventually goes to 0 at a over b. For instance, if the solution starts here, as we approach the line y equals a over b, it becomes horizontal. The tangent or the slope becomes horizontal. So we don't know what the solution looks like exactly, but we know how it behaves. It's going to behave like this. We have a family of solutions, of course, but all the graphs are going to look like that. All right, let's look what happened in between. Now let's skip that. So let's talk about it in a little bit. So this would be the region y is greater than 0 but less than a over b. And what happened to y prime? We'll look at it in a minute. But now we look at y is less than 0. What happened to y prime? Well, b times y, b is positive, y is negative, so that's positive, that's negative. A over b is positive, minus negative value, so that's positive. So negative times positive makes it negative. So, in this region, y behave the same way, or the solution behave the same way. But it started horizontally, right, at 0. The slope is 0, the slope is horizontal, y prime is 0, so it will go down, like so. So the solution is going to look like this. Every solution curve has these characteristics. So what we see is here we have a decay up to a over b. Here we have decay up to negative infinity, right? What happened in between? In between, y is positive, so by is positive, but a is less than y is less than a over b. So the difference is positive. So y prime has to be positive. Okay. So as such, the function will increase, but it starts horizontal and ends at horizontal, so it has an inflection point like so. This is not good. So how we determine of these infinitely many solution curves, how we determine what's what? Where is the solution? I'm sorry? You said something. I think you said it correctly. Initial value. Give me initial value. I know where to find it. So y prime, let me just finish. Y prime is negative here. Y prime is positive in the middle. And y prime is negative third region. Okay, those curves are a little bit screwy. I exaggerate in one direction, exaggerate in the other direction. So, give me initial value. Let's say when y equals, when x equals 0, y equals 1, I'll go right here. When x equals 0, y equals, let's say 1.5, I'll go here, right? When x equals 0, y equals -1, I know I'll pick up this curve. So you have a curve for each value, each initial value. The limiting capacity, if you look at the solution to the logistic equation or the logistic equation, it's the center area. You see, we start at something and we have a limiting capacity, which is A over B. Okay? Except in population, in the case of rabbits, we don't start at 0 because we need to start with somewhere, but technically speaking, you can start at 0 and finish at A over B. So that section is the solution of the differential equation that applies to logistic equation, which will be one of your projects, I think.
It's called logistic curve, right?
Logistic equation.
Called that way?
Logistic equation.
That kind of curve.
Logistic curve, yes. This is the logistic curve. I'm sorry, I didn't hear it correct. All right. This led me to the next topic that is related to that. One of the techniques we analyze autonomous differential equation is called phase portrait. This technique consists of the following. Let me first give you the definition. Again, it's not exactly a definition, more like a description. Phase portrait, it's a verbal definition. So the phase portrait is a graph consisting of a vertical line, which is the y-axis, critical points on the y-axis, and arrows pointing up or down, representing positive or negative values of y prime. Okay, so let's write it. So it's a graph.
Is it portrait? I think so.
Portrait, like face.
So the title is spelled right.
Portrait, no, it's portrait, sorry. A little bit of dyslexia. Portrait. not up and down, up or down. The phase portrait is a graph consisting of a vertical line, which is the y-axis, points on the line representing the critical points, and up or down arrows representing positive or negative values of y prime. Okay, let's take an exercise.
You can have both up and down arrows for a graph, for a phase portrait.
For each segment, it can
It's
be,
not either.
it cannot
or.
be both at the same time. Given the d y prime equals 4 minus y squared, 3 task, find its critical point. Part B. Sketch one possible solution curve in each region of y. All right, let's go to work on the first part. That's really easy. We let y prime equal 0, and therefore 4 minus y squared equals 0, and therefore y either equals 2 or negative 2. So let's write it as solution set like so. And on to part B. Part B, we do the same thing we did before in the example that I just completed. So if we let y equals 2 be this horizontal line, and we let y equals negative 2 be this horizontal line, we see that we have 3 regions. The 2 horizontal lines divide the xy plane into 3 regions. And we looked at what happened when y is greater than 2. When y is greater than 2, what happened to y prime? Well, if y equals, take a value, let's say y equals 3, then y prime equals 4 minus 9, so y prime is negative. Likewise, when y is less than negative 2, let's say y equals negative 3, again, 4 minus negative 3 squared is negative 5, so y prime is negative. On the other hand, if y equals a value between negative 2 and 2, let's say y equals 1 or y equals 0, then you have either y prime equals 3 or y prime equals 4. In any event, y prime is positive. So we can pick up only one curve this time. So it depends where we want the initial value to be. For instance, if I want to have y evaluated at 3 equals 0, y evaluated at 0 equals 3, then I have a curve passing through this point. So it will be this curve. Likewise, if I want y evaluated at negative 3, y evaluated at 0 equals negative 3, I'll have a curve passing through negative 3, like so. And if I want y evaluated at 0 equals 0, I'll have it run through the origin, like so. Okay, and this is a typical test 1 question. So part C, let's do the phase portrait. So vertical line representing the y-axis, there it is. Points on the line representing the critical points. So I have 2 of those. I have y equals 2 and I have y equals negative 2. And now up and down arrows. So the top region, y prime is negative, so it will be a down arrow. In between, y prime is positive, so it will be an up arrow. And down below, in the third region, we'll have a down arrow because y prime is negative, like so. We'll go back to it. Actually, let's say something now. I'm going to call this critical point right here, we're going to say that this is an asymptotically stable critical point, or we call it an attractor, because it attracts. On the other hand, this will be unstable critical point. Notice that the 2 arrows running away from the point, and therefore we call it a repeller. Notice that because the derivative is 0 at a critical point, and if you recall, the derivative is interpreted as a rate of change, right? So what does it mean the rate of change is 0? Let's say the rate of change is either acceleration or velocity, and it temporarily at a critical point is 0, then we say that the function is stationary, because there is no change when the derivative equals 0. Indeed, we call critical points, sometimes we call it stationary points. You see these terms. So this is a comment. So critical points are also called stationary. Okay, and now let's talk about stability of critical points, which I alluded here. So we have 3 cases. One is asymptotically stable critical point. Is it asymptotic in 1s or 2s's?
1s.
You sure? Two S's or 1s?
I would say 1F.
I can't
It
think.
looks
I'm gonna
like,
use one.
it looks like the root is symptom, so 1F.
The root is symptom, that is correct. I think. Yeah, it's 1S. Yeah, there is an acid asymptotically with 2 S's. That doesn't sound right. So let me change this here. That's interesting what you say. The root is a symptom. All right, so the way we already realized that it's this one. So this is also an attractor. And one way to simulate it, think about a wire that has a U shape. Okay? Thin wire, and on the wire there is a frictionless bed. Okay, bed without a friction. So at the bottom of the U shape, this is the most stable position, right? Now what happens if you push the bed to the side, one side or the other? It will slide back to the plate, to the stable position. Okay, so this is what we call a asymptotically stable system. Okay, so this is an attractor. The other is unstable, which you also saw on the left side. And that's, we also call it a repeller because we can see that if this is the critical point, the curve gonna repel out of it or away from it. So, well, this time, if we want to look at a similar simulation, again, this is the wire, but this time it's upside down. At the top, we can balance the bed on top, right? But it's sitting precariously. If we move it to the right or to the left, it's going to run away. It's not going to be back. Okay, and lastly, this is something we haven't discussed and we haven't seen yet, is something called semi-stable critical point. Okay, so there are two possibilities, both arrows pointing up or both arrows pointing down. I cannot give you a wire situation with both arrows pointing up, but I can give you a wire situation where both arrows are going down. For instance, if you can stabilize this here, but if you move it up, it will slide down back to the stable position, but if you move it down, it will slide away. Okay? That is the semi-stable. And